Now that we know absolutely everything there is to know about gases, it's time to apply what we know to our favorite topic, stoichiometry. So I want to kind of refresh your memory on what stoichiometry really is. Stoichiometry is the math that uses the coefficients from a balanced chemical equation to trade information from one chemical in and trade it out for another. And what unites all stoichiometry is the mole-to-mole ratio. What makes one form of stoichiometry different from another is how we get to the mole-to-mole ratio and then how we convert away from the mole-to-mole ratio. In all stoichiometry problems, there are two chemicals. Chemical 1 can be a reactant or it can be a product. It really doesn't matter. But our goal is to take that measurement for that particular chemical and to convert it into moles. Our second chemical, our goal is to take those moles and convert them back into a usable measurement, something I can actually go and see and touch and feel in the lab. So what if our chemical number 1 is a gas? What types of measurements can we take about that gas? Well, we've learned now that you can measure its pressure or its volume or its temperature. And you might be wondering, well, how do we convert those numbers into moles? Well, that answer is a little simple now. We know that we need to plug it into the equation PV equals nRT, pervnert. And when we plug in the numbers for P, V, and T, we should be able to chug back out N, or moles. Once you do that, you've effectively done the first half of a stoichiometry problem. And although it doesn't look like the stoichiometry problems that we've done before, because it hasn't involved field goal posts yet, it still is the same concept. We've converted our measurements into moles. If you would continue your stoichiometry problem at this point, you would simply take that answer of moles and put it over 1 and continue forward to your mole-to-mole ratio. And then you can be happily on your way to any of the other methods that you can go from moles back to a measurement. But what if chemical number 2, the second chemical, is a gas as well? Well, what pops back out of that mole-to-mole ratio is the unit of moles. So we would want to think about taking that number of moles and applying it to PV equals nRT to get some usable measurement again. So moles would get plugged in, and we should know and should be able to find in the room somewhere both the pressure and the temperature that the reaction is occurring at, so that if we plug in P and N and T, we should be able to chug back out volume, and that counts as our final measurement. So I know that this is kind of confusing, and I know that we're going to have to see a final example problem, so let's just hop right to it. Here's example problem number 1. How many grams of sodium chloride can be produced from the reaction of excess solid sodium with 1.2 liters of chlorine gas at 2.2 atm and 298 Kelvin? Again, already we're swimming in numbers, but you can clearly see that there is a chemical reaction in this problem. So stick to your training. Anytime that you see that they are calling for a reaction, write out the balanced chemical equation. This is a synthesis equation. So we have sodium plus chlorine, which is a Brinkelhoff, makes NaCl. Make sure you keep your state symbols in there and balance just like I have. The second step in my process is to take the numbers that they give you and layer them underneath each chemical to make the planning process a little easier. So first of all, I notice that they're asking for the number of grams of sodium chloride. So I'll write that underneath my sodium chloride. I also notice that they tell me that we're using excess solid sodium. Now remember that in chemistry ease, that fake language that we've been learning all year, that excess means ignore it in chemistry language. So we're not even going to worry about the sodium in this problem at all. Next number, 1.2 liters, that belongs to the chlorine gas, as does the 2.2 atms of pressure and the 298 Kelvin. So for planning purposes, we're going to start with the information for chlorine because we're given everything we need to know about that. And we're going to calculate too the grams of NaCl. So in this problem, chlorine is my chemical 1 and NaCl is my chemical 2. Time to take those measurements that were given about chlorine and try and convert them into moles. So I notice that it's a gas. I can see that from its state symbol. And I know the method for converting it into moles is to use the equation PV equals nRT. So I'll plug and chug the values I've got into that equation and solve for the number of moles, which just happens to equal 0.11 moles. Now I'm ready to apply my mole-to-mole ratio. So I'll take what I'm given and I'll put it over 1, and I'll apply my mole-to-mole ratio going from chlorine to NaCl. Moles chlorine on the bottom, moles NaCl on the top. My mole-to-mole ratio is 2 to 1. And now to finish the problem, all I need to do is to convert from moles back into my usual measurement of grams for NaCl. Now we've learned to do that way back in the dark ages with normal stoichiometry. So we'll simply go ahead and look up that molar mass and apply it. And you'll see 58.5 grams to 1 mole. Then we can start plugging and chugging and find our final answer of 13 grams of NaCl. So I'm hoping that you're seeing that, although there's a lot of stuff on the screen. If you are careful with your planning, stoichiometry doesn't necessarily need to be super duper hard. If you boil it back to what we know and kind of follow a routine number of steps, you should be able to break down these problems pretty simply over time. Now, one thing I should mention is that we have a special set of conditions in chemistry called STP. STP stands for standard temperature and pressure. And the reason that that is existing in the first place is that it gets annoying as you're writing down in a notebook constantly a certain set of conditions. And these conditions we usually use over and over and over and over again when we're setting up a chemical equation or chemical reaction in the lab that deals with the formation of a gas. STP means that your conditions are 1 atm of pressure and 273 Kelvin, in other words, 0 degrees Celsius. And that's pretty important, particularly when we do what we're going to do next. We're actually going to plug this information into PV equals nRT, and I want to plug in the value of moles as 1, just simply 1 mole. So in other words, if I have 1 mole of a gas at standard temperature and standard pressure, what volume will it occupy? So I plug it in, chug it back out, solve for V. I find that that volume is 22.4 liters. Now that is a magical number for chemistry because it tells me the relationship between volume and moles under STP conditions. We call this something very special called standard molar volume. And it basically tells you that 1 mole of any gas at STP will occupy that volume of 22.4 liters. Now, because we can write this like an equivalent statement, that 1 mole will now equal 22.4 liters, but only at STP, we can use that as a conversion factor. So I can present that as 1 mole per 22.4 liters, or 22.4 liters over 1 mole. Now that's really neat when we go to apply this to what our stoichiometry problems could actually look like, because now we might have a little bit of a shortcut method for some problems. So again, back to the drawing board here, back to planning for that mole-to-mole ratio and how we're getting there. So let's say that a problem tells you that you have a gas at STP conditions. What that enables you to do is kind of take the fast track. You're going to look for the liters of that gas at STP, and you'll be able to set up field goal posts and put those liters over 1. And STP, or that standard molar volume, is almost like how we have molarities for our liquids. It's kind of like a weird molarity for a gas, but it's a gas, it's not a solution. But our liters can cross down to the bottom, and we can replace that with moles up to the top. And that relationship is always going to be the same under STP conditions. It's quite literally, you can apply it to every single gas. It doesn't matter what the gas is. It will always occupy 22.4 liters for every 1 mole. So you can effectively cut out that algebra step of Pervner as long as you're at STP conditions, heading straight to that mole-to-mole ratio. If your second chemical is also a gas at STP, you can kind of apply the reverse of that fraction. So moles would be popping back out of that mole to mole ratio. So we'll put moles on the bottom to be able to cancel out, and then liters up to the top, and apply that molar volume, 22.4 liters to 1 mole. And out the back of that problem should pop liters of that gas under STP conditions. So just to make sure that you understand the difference between these two methods, you're going to employ PV equals nRT for any gas that's not at STP. So it's not at 1 atm, or it's not at 273, or it's not at either. But if the problem specifically states that your gas is at STP, you can apply the second bottom method here, which is a fast track method for getting your stoichiometry problem done. However, for every single problem, the PV equals nRT method will always work. The bottom method only works under specialized conditions. Time for another example problem. Here we go. How many grams of sodium chloride can be produced from the reaction of excess solid sodium with 1.2 liters of chlorine gas at STP? So again, let's plan ahead. And what I notice most prevalently is it says STP. We rejoice. Hooray! It's at STP. This should be a fast problem. We want to start with that balanced chemical equation. That's really critical. And layer the information for the problem underneath. It's asking for the number of grams of NaCl, but it also provides us with 1.2 liters of Cl2 at STP. And just like before, that means that my problem will begin with the Cl2 and end with the NaCl. There's my chemical 1 and chemical 2. First step. Take the information I'm given and convert it into moles. But because it's at STP, all I have to do is take my 1.2 liters, let liters cross down to the bottom to replace it with the moles on the top, and that relationship for this gas at STP is 1 mole to 22.4 liters. Now that I'm in moles, I can apply my mole to mole ratio from chlorine to NaCl, that's 2 to 1. And for my chemical 2, since it's a solid in grams, I can go from moles directly to grams using the molar mass. Plug and chug, you're ready for 6.3 grams of NaCl.